kind of how that goes. All right. So a couple of quick definitions here. pH 2. Okay, that's going to be pretty acidic. Okay, I think that was around lemon juice, something like that. Okay, so not enough to really hurt you, but not something you want to squirt in your eyes. In other words, that'll orient you a little bit towards what pH 2 means. pH 2, what that means is that the hydronium ion concentration, remember square brackets means molarity, it means 10 to the minus 2 molar. And what does that capital M stand for again? Something per something? Moles per liter. Okay. pH of 2 means 10 to the negative 2 moles per liter. So it might be nice for us to have a little review of what how those powers of 10 work. Okay. Anything to the 0 power is just 1. Okay. Because remember, when we're taking powers, we're multiplying. So sort of the transparent multiplying thing is 1. So that's what 10 to the 0 is. Okay? 10 to the minus 1 is 1/10. Okay? Negative powers of 10, or negative exponents, put it down on the bottom of a fraction. Okay? So 0.1. What's 10 to the minus 2? Yep, 0.01. It would be 1/100th. 10 to the minus 3, 1/1000th. 0.001. Okay. So putting that in decimal, which makes it a little easier to envision, 10 to the negative 2, that's 0.01 molar. So we're dealing with a fairly small concentration. Okay. 0.01 molar. That means those hydronium ions, if we had a liter of solution, we'd have 0.01 moles of those hydronium ions floating in that particular solution. Okay? But it's not just about moles, it's about concentration. So it's about how close those hydronium ions are together within that solution. Right? pH of 3, if we kind of follow that same pattern, it's 10 to the minus 3 molar. That's 0.001 molar. Okay? Now, just based on what we talked about with the pH scale, what should be more acidic, pH 2 or pH 3? Yeah, pH 2 is like lemon juice, pH 3 is like vinegar, something like that. I think that's what it said, right? Yep. So it's towards the more acidic end of the pH scale. We've got a pH scale that you can refer to there. But we can also refer to those concentrations. Okay? pH 2 is 0.01 molar, is more concentrated. It's 10 times more than 0.001 molar. Okay? That's pH of 2. That's pH of 3. So, because we're going to be dealing with very small concentrations that change by huge amounts, the pH scale is a way of just sort of turning those powers of 10 into convenient positive numbers. Okay? So it's no coincidence that we have these same numbers in here. In fact, that's sort of the definition of pH. Okay? pH of 2 is 10 to the negative 2. pH of 3 is 10 to the negative 3. Okay? What if our concentration was 10 to the negative 9? Okay? Is that more concentrated or less concentrated?
Really basic.
Yeah, well, it's going to be more on the basic side because that's 0.0000. It's 8 zeros with a 1. Okay? So that's pH of what? 9. Okay? That's the same relationship that we just did there. Okay? Let's look at our little scale here. Okay? 10 to the negative 2 molar, 10 to the negative 3 molar, 10 to the negative 9 molar, neutral, 10 to the negative 7 molar. There's something special, right? And we're talking about concentration of hydronium ions. There's something special about the relationship of hydronium and hydroxide at neutral pH. That's when their concentrations would be the same, and that concentration would actually be 10 to the negative 7, okay, in a neutral solution. Okay. So if this is 10 times more acidic, what if we went from 4 to 2? How many times more acidic is that? 20? Can't fool you guys. Okay, so this is a logarithmic scale. Where a change of 1 unit on the pH scale means a 10-fold, a 10 times change in the actual real world, okay, of concentration. Okay? So 10, 100, 1,000, 10,000, okay, we're going by powers of 10 every pH unit we're changing. Okay? That's because these actual concentrations go through a hugely wide range. Our hydronium concentration is so low when we're basic, okay, because our hydroxide concentration is now the thing that's getting larger. Okay? Even when we become very acidic, right, we're talking pH 1.1 molar. Okay? pH 0 is 1 molar. So if we had a concentrated acid that was maybe 6 molar or 12 molar, that would actually be a negative pH. Okay, it turns out. So it's possible to get lower than pH of 0. Those are the really harmful things. Okay? But the things that we would encounter in real life would be 0 point something molar. Those are the pHs that are somewhere 0 or above. Okay? So let's just talk a little bit about how a logarithmic scale works. What we just did there, we said 10 to the negative 9 molar, that's a pH of 9. Okay? We just took the opposite sign of the exponent. Right? What a logarithm does, you may have learned a little bit about this in a math class at one point, and it's probably just a key on your calculator at one point, but the concept of a logarithm is not a terribly difficult one. Okay? Look at this quick definition right there. The logarithm of 10 to the 9 is just 9. So the logarithm says, to what power did we raise 10? Okay? That's a standard base 10 logarithm. There are other bases, like the natural logarithm has the base of e. Okay? But a regular base 10 logarithm just says, to what power, to what exponent did we raise 10? Okay? So what is log of 10 to the 2? 2. When it's an exact power of 10 like that, you do not need your calculator to do a logarithm. Okay? It's just saying, what was the exponent? What's the log of 10 to the negative 9? Yeah, it's just negative 9. It's just to what power did we raise 10? Okay? What is the negative log of 10 to the negative 9? Positive 9, absolutely. And you'll notice right here is the math that we just did. We took 10 to the negative 9 and made it into 9. Okay? So that's what the definition of pH is. pH is the negative logarithm of a hydronium ion concentration. Okay? And if it's an exact power of 10, it's just the opposite of what the exponent was. Okay? So if our hydronium was 10 to the negative 6 molar, pH is the negative log of 10 to the negative 6, which is just 6. Okay? That's right here. Okay? If we have a number in scientific notation, like we usually do for a concentration, 1.0 times 10 to the negative 12, pH is negative log 1.0. I'm going to use E sort of from now on, but that just means, remember, times 10 to the negative 12. Okay? If we didn't have that 1.0 there, it would be just like the problem above it, right? If all we saw was the 10 to the negative 12, our pH would just be what? Yeah, just be 12. Okay. The difference here is that now we added significant figures. Okay. In scientific notation, the sig figs are these numbers off to the front. Okay. There were no significant figures here in the power of 10. Okay. So we got this exact number based off of the logarithm there. When we add these two significant figures to the front, we need to add 2 more digits to our answer over there. But since it was 1.0 times, we're not going to change the size of that value. So how do I add 2 digits to 12 but not change its actual value? We do that all the time when your calculator doesn't give you enough numbers. What do you think? How do I add 2 digits to 12 but not change its value? That's like a riddle. And we don't even need scientific notation. We can just keep it in regular, plain old standard notation. 12.0. Yeah, we got. If it was just 1 times 10 to the negative 12, we'd call that 12.0. 1.0, we've added 2 sig figs here. We need to add 2 digits over here that, what do we call them when we're specifically counting how many digits are after the decimal point? What would we call those? What do we, trailing zeros? When we're counting the number of digits to the right of the decimal point, we call those decimal places. Okay. That's the only slightly fiddly thing about this process here, is that when we take a logarithm, okay, the significant figures that we started with show up after the decimal point. Okay? But that's because the numbers before the decimal point of this number that we got from a logarithm, those came straight from the power of 10. Those came straight from the exponent. Okay? So as long as you remember that if you take a log, your answer has to have decimal places that come from the sig figs. Okay? The sig figs turn into decimal places, then you'll sort of be fine with it. Okay? Now, if we've got a number that's not an exact power of 10, that's where we need to use our calculator. But first, we can compare. This number here is more concentrated than the one above it, right? This is 1 times 10 to the negative 12. That's 4.2. That's 4.2 times more concentrated, right? It's 0.00000000042 instead of 0.00000000001, right? So this was pH 12. This one has more hydronium in it. So is that going to be a higher pH or a lower pH? What do you think? What direction do we go when we have more hydronium, when it becomes more acidic? Yeah, this is actually going to be 11 point something, okay, because it's going to be more acidic. And we can predict that, at least. Okay? Anything more acidic than exactly 10 to the negative 12 is going to be a pH of 11 point something, because that's the direction that we go on that scale. But to get the actual number, we need to use our calculator. So get your calculator out. And there's sort of 2 ways to do this based on what type of calculator you have. But either way, what math we're going to have to do is negative log of 4.2 times 10 to the negative 12. Okay? So if you have a 2-line calculator or a graphing calculator, you're just going to pretty much enter exactly that. Okay? Make sure you use the negative sign, not the subtract, but the negative sign, log 4.2, and then make sure to use the E or whatever, E or EE or EXP if you have it for entering the power of 10. Okay? Let me show you on my camera over here. This graphing calculator will behave the same way that any 2-line calculator would. Okay? So I can just do, here's the negative log 4.2. On mine, I've got EE printed right up above there. Some calculators have that as a button. Some have EXP down on the bottom. But I did E negative 12. And 11 point something. There's something wrong with my screen, but I typed 4.2e minus 12. Okay. So going to answer something like that. If you have a single line calculator, you have to kind of work backwards. What I called a numerical calculator on the notes there. You always have to start with the scientific number. So I'm going to do 4.2e negative 12. Okay, looks like that. Make that just a little brighter. But I did EE. Okay. That means 4.2 times 10 to the negative 12. Okay. It's not just 4.2 to the negative 12. It's 4.2 times 10 to the negative 12. Okay. So I have that number. The switch the sign button toggles plus or minus on the last thing that you entered. Okay. So the little plus, the little minus appearing and disappearing there. Okay. So that's 4.2 times 10 to the negative 12. Then I'm going to take the logarithm of that. So you hit log, and then you switch the sign of your answer. So you're starting with, to do that math, you start with the number, right? Then you take the logarithm of it, and then make it negative. So you should all have gotten an answer that's 11 point something. Well, that's the question, isn't it? Because the number we started with had two significant figures, okay, in the scientific number there. Oops, sorry. I have to do my little hotkey here. There we go. The number we started with has two significant figures in the scientific portion of it. And then what did we say is the special thing we do when we take a logarithm of a number? What do those significant figures become? They become decimal places. Okay? So the two significant figures that we started with turn into two decimal places. So our actual answer is going to be 11 point what then? Yep, 11.38. Two sig figs. We take the log. Becomes two decimal places. Okay? So anytime you're given a concentration of ions and you need to do a p-value, the p function is taking the negative log of that value. So hydronium ions are a concentration with a unit in molar. pH is just a number. pH has no unit to it because it sort of came from the exponent. Okay? So that's what we do. pH is our answer. We get a pH by taking the negative logarithm of a hydronium ion concentration. So I want you to do that with this one right here. Take the negative logarithm of 2.87 times 10 to the negative 3. And see if you can punch that in your calculator and get an answer and round it to the right number of digits. And let me know if you're having any kind of trouble with your calculator. If you got a graphing calculator, you just punch it right in. If you got a two-line calculator, same sort of thing. You just kind of punch it right in. If you have a single line calculator, you have to start with the number. Yep. Yep, you start with the number, then take the log. Yep, take the log, let's switch the sign. Yep. Anybody having any calculator issues? Make absolutely sure that you practice this on the kind of calculator that you'll be using on the final exam, okay? Because it's different on different calculators. If you don't have a calculator, go to Walgreens or whatever, pay the $10 to get a calculator just so you can practice this, so you know how to punch these in. You're going to have to do this on the final exam. So what was our answer? Yep, 2.542. In pH values, the sig figs are after the decimal point. That's another way of thinking of it. Because we have those 3 sig figs here, they become these 3 decimal places. Okay? So we'll get a little more practice doing that as we go on. But let's right now go in the reverse direction. Okay? What if we're going from pH to a hydronium ion concentration? Okay? If pH was 8, what would the hydronium ion concentration be? And you don't need your calculator, again, for exact pH values. You don't need a calculator. Hydronium ion concentration is going to be 10 to the what for this one? Yep, you got it. -8. And these concentrations have a unit. It's molar. So don't forget the unit when you're solving for a concentration. Okay? Here's the equation, but that's pretty much just exactly what we did. Hydronium ion concentration is 10 to the negative pH. 10 to the power of the negative pH value that you were given. So if you're given a non-exact pH value, something with decimals to it, it's just going to be 10 to the negative that, okay? 10 to the negative 2.87. But this is not proper scientific notation. Okay? It needs an exact exponent to be scientific notation. So that's where we need to use our calculator again. Okay? We're going to do 10 to the negative 2.87. So on a 2-line calculator or graphing calculator, probably the easiest way on a lot of calculators, printed right above log is 10 to the x, because that's the opposite math for a logarithm. Taking a log going one way is the opposite direction of doing 10 to the power of going back the other way. So I just do second log. It gives you a 10 to the 2.87, or was it 2.87? Yeah. Okay. The other thing you could do that's completely equivalent, you could do 10 and a caret. Okay. Mine has a little caret that just raises it, so make sure to have the negative sign in there, though. On a numerical calculator, though, the single line, remember again, you have to start with the number. On a calculator with just one line, I have to do 2.87. Okay? You have to do switch the sign to make it negative, and then you absolutely have to do this second log. Okay? That takes 10 to the power of the number that you've entered. Okay? So it's sort of working backwards, but you do second log. Okay? That gives you a number like that. These numbers usually are given in scientific notation, so you can always put your calculator into scientific mode. Single line calculator, you can always do the second psi down here. That puts you in scientific mode, and float puts you back in regular. Okay. Graphing or 2-line, hitting mode. Okay. A lot of them have mode. Some of them have psi/engineering up there in the upper left. I'm going to go over. I'm going to hit enter there for scientific, and you have to quit. The battery just died on that one, but I'm done with that anyway. You can put it into scientific mode, and that's actually useful if it doesn't have enough digits to it. Okay. Now, the issue here is that we're starting with the pH. So remember, the sig figs are already over there after the decimal point, and it'd help if you could see what I was writing again. Do that. Okay. Remember, pH values, the sig figs are after the decimal point. Okay. So when I do a number over here, I need a number that has 2 significant figures in our answer. So it's sort of the reverse of what we were doing before, okay, where the pH value at the end before had the decimal places. Now we're starting with the pH value. These will turn into the sig figs of our concentration. Okay? So it's just going backwards from what we did before. So what would be the answer rounded correctly for this one in scientific notation? 1 point something? Is that what you guys got? You guys get it into scientific? 1.35. Well, we only want 2 sig figs, though. Yeah. Let's do 1.3. 10 to the negative 3 molar. I'll put the dots down here. Okay. This is a concentration, so its sig figs are recorded just normally like any other numbers sig figs would be. Okay. The special thing comes in this pH value, because at the beginning of a pH value, that sort of came from the power of 10. Okay. So that doesn't really count. It's those digits that give us 2 sig figs of the concentration over there. So why don't you guys try that with pH of 6.43. To do that, it would be 10 to the what? But then you need to use your calculator to evaluate exactly what that would be. Now, if your calculator fills up with zeros, you need to force your calculator into scientific mode so that you have enough significant figures. Use mode or psi, something like that, to get it into scientific notation if it's filled up with zeros. And you're going to do this one here. You're going to start with the number. You're going to start with 6.43. Yep. Yep, there you go. Okay. So if you did 10 to the negative 6.43, how many significant figures should this answer have? Should have 2, because that was a pH. In pH, the sig figs are there. What did you get rounded? 3.7, 10 to the negative 7. And what unit? Molar, capital M. Okay. Concentrations. Okay. H3O plus in square brackets, that's a concentration. You need to include that molarity unit. The pH has no unit. Okay. Molar is the unit of that. So what you can do to practice is just go back and forth. We could take the negative log of this and bring it back to a pH. And then we could do 10 to the negative 6.43 and bring it back. Okay. So that's just going back and forth 2 directions for pH and hydronium ion concentration. Okay. So let's go on to OH. Remember, hydronium was the acid ion, the ion created by acids. Hydroxide is the ion created by bases, and those two have an inverse relationship with each other. Okay? But we can perform all the same calculations with OH that we did just like before. Okay? So if you're given a hydroxide ion concentration like that, the P value is now POH. It's not pH, it's POH. Okay? Going this other direction. So if hydroxide is 10 to the negative 4, POH is 4. So we've got these equations here that look exactly like the other 2 equations that we had for pH. Okay? It's just instead of hydronium, we're talking about hydroxide. Okay? So if we take the negative log of a hydroxide, that gives us a POH. If we do 10 to the negative POH, that gives us hydroxide ion concentration, exactly like the 2 calculations that we did on the last page. Okay? The new piece of information right here is the relationship between pH and POH. So take a look at these 2 scales over here. 7 is neutral, for both of the scales. Okay? And we can draw an acidic arrow going towards pH of 0. But since they're opposite, acidic means higher pOH. Okay? Means lower pH but higher pOH, just because the scales are opposite. They've sort of been flipped. Okay? And basic, so the more acidic we get, pH approaches 0. The more basic we get, pOH approaches 0. Okay? But to calculate one from the other, just look at any pair. Okay? Look at the relationship between pH and pOH. For any solution, what does pH plus pOH equal to? See that? 14. pH plus pOH is 14. That's because these scales go from 0 to 14 centered at 7. Okay? So when we pivot one of them, still keeping it centered at 7, that means the sum of those two will equal 14. So sort of a unique property of water solutions, okay, that it has to do with that 14 number. So if you're given one, you can get the other just by subtracting from 14. Right? If I have a pOH and I want a pH, I could just subtract pOH from both sides, right? So 14 minus pOH, or okay. So all we need to do is that 14 minus in order to get from one to the other. So if you ever find yourself on the wrong side of a scale, if you're talking pOH or pH or hydroxide, but you want to be hydronium or pH. Okay? You have to do this kind of conversion to get from one scale to the other scale. Okay? So let's just review here. I've got a little road map. These two are just what we had on the last page, right? Hydronium ion concentration and pH. If you're given a hydronium ion concentration, that was the first calculation that we did today. Okay? Like 10 to the negative, let's just do a quick simple example here. 10 to the negative 4 molar. If we do one with an exact concentration like that, you can do these calculations in your head. Okay? So if hydronium ion concentration is 10 to the negative 4, what would pH be? pH would be 4, because what we did was take the negative log of the hydronium ion concentration. That says what was the opposite of that exponent? 4. Okay? So here, pOH is 10, because what math did we do there? Yep, we did 14 minus pH. Okay? And if pOH is 10, what would the OH minus the hydroxide ion concentration be? How do we get a concentration, right, from a p-value? What do you think that would be? Yep. It's going to be, we're going to go 10 to the negative pOH. It's going to be 10 to the negative 10 molar. Okay. Then going in the reverse direction, how do we get that negative exponent into just a number? What did we call that math? Negative log. Okay. How do we turn 10 into 4? (14 minus pOH). Okay. And then how would we turn this pH of 4 into 10 to the negative 4? Well, it just says it pretty much right there. 10 to the negative pH. Okay. So that's a general roadmap that should be able to take you through any of these values. Okay? I'm just going to, here, let's put parentheses around those actual values so you don't get them confused with equations. It's just an example. Okay? Should have made that a different color. But what we've got above and below those arrows, that's the math that you do for any value. Okay? that can get you from one end of this to any other side. So let's try that just with this set of calculations right here. Let's say we're given hydroxide ion concentration 0.0230 molar. Okay? That means we're starting over here. Okay? What math do I do to turn that into POH? Take a look at the roadmap there. If we're starting with hydroxide, what do we have to do to get it into POH? We're going to do the negative log 0.0230. Okay. So punch that in. You get a number. Literally what that P function means, and I don't remember why it may have come from power or something like that originally, but in math, the P function means take the negative log. Okay? So to go from hydroxide concentration to POH, we take the negative log of that value. POH values, just like pH values, we count the decimal places. The decimal places are the sig figs, essentially. So how many decimal places should this answer have? How many sig figs did we start with? We started with 3 sig figs. Leading zeros are not significant. If this was in scientific, that would be 2.30 times 10 to the negative 2. And you can always see sig figs very clearly in scientific notation. Molar. Okay. So what would this answer over here be with 3 decimal places? It would be 1.638. It'd be something like that. Now, I'm going to write a couple extra digits there because your calculator had at least more digits, right? It had 27 something after that. Okay? But if this was our final answer, we'd put these 3 decimal places right there and call it 1.638. The thing is, when you're doing one calculation after another, you cannot use your rounded value in the next calculation. Your answers will just kind of get wronger and wronger the further you go using rounded values. So what would be best would be to keep that number, that whole thing, in your calculator, okay, where your calculator should be totally filled up as much as possible, and actually use your calculator to do the next calculation. Okay? What do we have to do to turn POH into pH? Well, we have to do 14 minus that value. So if you have a graphing or a 2-line calculator, down on the lower right, there's something ANS, answer. Sometimes it's over second, okay, over something in the lower right. Take advantage of that, because what that does is insert the answer to the previous calculation. And then you never lose any digits or anything. You always use your full unrounded value for the whole thing. If you don't have that, make sure to type in at least a couple of extra digits, okay, so that you're not using your rounded value. So I would do 14 minus 1.63827 at least. Okay. So uh, 12.36173, something like that. But if that was our final answer, we would keep those 3 decimal places, right? I mean, if that were being rounded, it would be 12.362, because when you subtract, you keep the decimal places. So then what's the last thing we have to do to go from pH to hydronium concentration? Take a look at the roadmap again. We have a pH value, pH of 12 point something. I want to know what that hydronium ion concentration is. So what math is that? Yep. So here, if you have it, do 10 to the negative answer. That will insert the answer from your previous calculation, if you have it. That would insert this whole thing from up there, and you'll have a nicely precise answer. (4.34782), something like that, times 10 to the negative 13. But this one, we absolutely do have to round, because that's our final answer. It's molar. The p-values had decimal places. The concentrations will have that same number of significant figures. Okay? So the molarities, the concentrations, the square bracket ones, those have sig figs. The p-values have that same number of decimal places. So this is a concentration, so it's going to have sig figs. How many sig figs? Yep, 3 sig figs. So what would it be? 10 to the negative 13. That would sort of be our final answer of that entire string of calculations. Okay. If we were giving intermediate values for any of these, they would have to be rounded. Okay. But use the unrounded, the complete value, if you're doing one calculation after another. That makes sense? So if our question was just what is hydronium, okay, you'd do that string of calculations, keeping the unrounded values in. Okay? Otherwise, you get more and more error as you go. If you're asked if a solution is acidic, basic, or neutral, it's easiest to look at the pH. pH at 12 point something, what does that mean about the solution? Yeah, it's basic. Here's our pH scale. 7 is neutral. There's the acidic end. Here's the basic end. We were writing here pH 12 point something. Okay? So pH greater than 7.00 is a basic solution. Okay? Does anybody have any questions about where we got some of those numbers? This is going to be something you'll have to do some practicing with in order to make sure that you can get these things punched in your calculator. You're going to have to do calculations like this in your mastering chemistry. Okay? So make sure to get started with that right away. I'm just going to show you sort of one more thing with the exact same type of calculation, but this question is just a little bit different because instead of just giving you one of those 4 values to start with, this is a question that asked, what are all 4 of those values for this particular concentration of HCl? Okay? That is a specific solution. It's a specific solution with a concentration. So if you ever run into a question like that where you're given a concentration of this particular substance and you're asked one of those questions, first thing you have to do is decide if it's an acid or a base. So what is HCl? Sure. It's hydrochloric acid. Its formula starts with an H. Okay? It's an acid. So if the concentration of HCl is 1.50 times 10 to the negative 3 molar, which of these 2 concentrations here will that be the same of? Which ion do acids produce? Yeah, acids produce hydronium. And like we said before, for simple acids like that, every 1 mole of acid produces 1 mole of hydronium ions. So 1.50 10 to the negative 3 molar. So that's what you're given. What you would have to do then would be to start with that value and do pH, pOH, and hydroxide. Okay? And we're not going to do that right now. I will have those values in the notes that you can download, but you should definitely practice those to make sure that you can get through that. It's going to be the exact same as what we did on the last page. The thing that will be provided for you on the final exam are those equations shown exactly right there. So as you're doing these calculations, you should get used to looking at these equations and using these to do that math. Right? For instance, if I'm doing a pH, I'm going to look for this one right here. My answer is going to be a pH. So to do that, I have to take the negative log of hydronium. Okay? So I just show you the sum here. That means the same thing as one of these will equal 14 minus the other. Okay? But I just show you that their sum is equal to 14. Okay? The only other situation right here, here's a similar kind of question, but here's a concentration of KOH. Is KOH an acid or a base? It's a base because of its hydroxide. Okay? So concentration of KOH given in the problem was 2.43 10 to the negative 5 molar. Of our four kind of calculations we did here, what will that be the same as? What is the ion that bases produce? Yeah. So as long as it's a simple formula, as long as there's just one hydroxide in that formula, KOH concentration is just the same as hydroxide concentration. Okay. From there, you would have to do POH, pH, and then you could do hydronium. Okay. But that's definitely something that you need to put a little bit of practicing into. In the content area of Brightspace, I have a practice worksheet. Way down in the bottom here, pH calculations. This, I guarantee, will give you all the practice you need for doing any pH calculation. It's just formatted as a table. If you're given one of these here, you should be able to calculate the other ones and then tell whether the solution is acidic, basic, or neutral. There are a couple of them that have, where is it? Here. A couple of starred ones like this. Perform the starred calculations without a calculator. Those ones are exact powers of 10. Okay? So I can just tell you right now that would be a POH of 7 because we had 10 to the negative 7 of hydroxide concentration. So go through those, but that can be a little quiz for you to make sure that you can enter those values properly in your calculator. We just got one page left here.